Okay, so I have solved all four problems. The contest is still going on. So let's quickly go through them. So problem one, check good integer. So here we're given an integer. We have to find the sum of its digits and sum of square of its digits. And we have to tell if that difference is greater than equal to 50. So this is a simple implementation problem. We take the sum and square sum of squares and we find each digit. We add it into we add a digit in a sum of digits and we add the digit square in the sum of digit squares. So n divided by 10. So we have uh, already used that digit and modulo 10 will give us like the last digit. If we divide it by 10, then what is the remainder? So that is the last digit, and divided by equal to 10 will just like ignore the last digit, remove it, and we loop on this until n is positive. And then we tell the final result if the s sum of squares minus sum of digits is greater than equal to 50. Yeah, so that is the first problem. Second one. Okay, so here we are given an array and uh, a subarray is called frequency balanced according to this condition. If it contains either it contains only one element, if not, if it contains at least two elements, then the frequency should be only two, like if we see the frequency of each number, it should be either the smaller one or the larger one, and the smaller should be half of the larger. So if we see this example, here we have 2 1 2 3 3. So here we have more than one number. So 2 appears twice, 3 appears twice, and 1 appears once. So the larger frequency is 2 for these two numbers, and the smaller frequency is 1, and the larger frequency is double of the smaller one. So in that case, this is a good subarray. But if we see here, like if we choose this entire subarray, then we have at least two elements. Yeah, so if we have at least two elements, but the frequency of all of them individually is 1. So and there is no no distinct smaller and larger frequencies. So in this case, this will not be considered. Like the statement is a little ambiguous as I felt, but yeah, like in this case, it is all fives. So we have only one unique number. So 5 is fine. Yeah, so a statement is little ambiguous in that sense, but if we go to the implementation, since n is 1000, the length of the array, so we can check this for every subarray. So that's what I've done. I run I from 0 to n and j from I to n. So basically this will check all the subarrays. Now for each subarray, I will maintain the frequency. So this will store the frequency of each element and another map which stores the frequency of the frequency. So let me take this example. If I take 1, 2, 2, 1, 2, 3, 3, 3. Oh, that's fine. So frequency and frequency of frequency. So we take 1. So frequency of 1 becomes 1, and this of 1 will have a frequency of 1. So this is the number in the array. This is its frequency, and this is the frequency. This is the frequency of frequency. Like how many numbers have the frequency of 1 in that sense. Yeah. So and go ahead. If then we go to 2, so 2 will appear once. Now two numbers have a frequency of 1, so we'll update it to 2. Then we have this 2, so now 2 will have a frequency of 2, and so now only one number has a frequency of 1 and one number has a frequency of 2. So we maintain it accordingly, and then we check the condition. So this is how I've maintained it. If it con so like in this case, as you saw, like initially one's frequency was 2, but since 2 appears again, we have to remove this, so we can add it here. So that's what I've done here. If the number is already present, then in the frequency we reduce it by 1, and if it is 0, then we remove it from the map, and then we add the frequency and the frequency again. then the condition would be if frequency dot length is 1. If there's only one unique element, like in case of this 5, or if we find this condition, then that there are at least two sets of unique frequencies, and the first one, double of first one, is equal to the last one, the second one. And in that case, it is a valid subarray. So we maintain the answer and we store the length of a subarray in the answer. We take the maximum basically, and then we return it at the end. So yeah, this is problem 2. Problem 3. Okay, so here we are given uh, n devices and each device has some units, and it is given that from each device we can remove exactly one unit and add it to end of some other device. And then we have to tell the maximum, we have to tell the sum of the minimum capacity of, uh, let's say, the sum of the minimum unit size in all the devices. So if we see this example, I take this one and put this at the end. So I get 1 plus 3 equal to 4. Yeah. So the idea is that, first of all, if we see the constraints, then uh, the number of units can be 1 as well. So if there is only one unit in each device, so if each device has only one unit, then it makes sense to take that unit only. It doesn't make sense to remove it, otherwise it will be 0. So that's what I've done, first written here. If m is 1, then I return the sum of all elements. Otherwise, it is always better to remove the smallest element from each uh, device. So let's say these are the devices and these are the units sorted. So if this is the smallest one, then it is always better to remove it and take this one. Remove it and take this one, and so on. But we cannot do that for every device. So this is like the smallest value, and this is like the second smallest value, right? So what we'll do is we remove all these values. Then our answer will be some of these, but days have to go somewhere. So we will put them instead at the place which is having the smallest, second smallest value. So let's say this was, let's say 1 1 1 1 1 2 3 4 and some other values. So we remove all these one from the machines, and let's say take it 5, let's say. And now in the second smallest values, if it uh, oops, if we decide to put all the ones at here, then it will be bad because instead of 5 we have to take 1. So for this so this is a bad idea, so we take this 2 instead, because this is like the smallest value among these. So instead of 2 we take this one. So this is like an answer. So if we see the implementation, I maintain an answer, I maintain the minimum value, so this is like the smallest value among these, and this is like the smallest, second smallest values. This is smallest among the second smallest, this one. So this is this min and min sec. So this is the smallest among here and here. So now I iterate over each array, I sort it. Like sorting is strictly speaking not necessary. You can just find the maximum smallest and second smallest. But yeah. So answer plus equal to unit of 1. So this is like the second smallest value I'm adding to my answer. And I'm taking the smallest of the smallest and smallest of the second smallest. Now I I will remove this value. Let's say min sec is going to be 2 here and min is going to be 1 here. So I will remove this from my answer and I will add the smallest value from into my answer. So yeah, that is the idea why we are removing this, because we are going to consider this here. So I hope that makes sense. Coming to the last problem. Okay, so this was a good one. So here we are given an array, an integer k, and we are allowed k swaps on the array. Then we have to tell the maximum sub-array sum we can make. So it took me some time to come to the idea. If we see the constraint, then the length is 1500 and the elements are like 10 power 5. So I'm not sure why they asked I64 here. I think the sum should fit in a I32 value. Something like 1.5 into 10 power 8 should have fit into I32. But anyway, so the way I have approached is using binary search. So for like there is going to be some the sub-array sum possibles, like let's say in a general binary search idea. So let's say this is an answer plus one and so on. So till this value we will have a binary search, like is it possible to at least make this sum. So our predicate is going to be for some x, if we can make this, if we like can get sum greater than equal to x. So it is going to be true for all these values up until the answer, and it is going to be false for answer plus one. So we are finding the last true. Okay, so that is the first observation. So I have taken binary search dot last true. So I have run it from 0 to infinite because I actually realized uh, my midpoint implementation is a little incorrect when it little different when it comes to negative numbers. So I have taken it from 0 to infinite, like infinite is 10 power 11 here. One observation before that is if it has all, it does not have any positive element, then the answer is obviously going to be the maximum element in the array. So that's one thing I've handled as an edge case here, and I'm only checking for positive sub-array sums. Okay, so continuing with this, this is going to be a predicate function. Now, how to find this? So since the constraints were small, like n is 1500, I decided to iterate over each subarray and check if it can make a sum like that. So the observation is, okay, let's say this is like a subarray. This is the entire array, and we choose this subarray. So it has one, it has minus one or two, let's say minus three or two, or something like that. So in this is mostly to consider what all negative elements I am considering at max. So if there is a 4 here, I can swap it here and get the sum of 7, right? So it is always better to choose values like this. But let's say there is a minus 4 as well, or let's say a minus 1 as well. Then in this case, the sum will be 6. But in this case also, we remove the smallest value with this. Or let's assume we only let if k is equal to 1, then this is the ideal scenario. So for each like this, for each subarray, I'll find a maximum sum I can create. So how I've done it? I have maintained all the positive numbers in a set. Let's go to the implementation. This will make it much clearer. I maintained all the positive numbers in a set. If there's no positive number, then we return the max as explained before. Now I'll take the sum of the first k elements. So I will remove the last value, the largest value from the set, and I'll add it to our answer. One thing to observe is that the number of positive elements can be smaller than k. So that's why I've taken I maintain a taken count as well with what I'm updating the k in the future. So I'm going to get set k as taken afterwards because like a larger k doesn't make sense. We're not going to swap negative values. Okay. So yeah, so we have maintained the sum of the largest k values, k adjusted values technically, and then we run a binary search. So we run over each subarray as we have done before, from I from 0 to n and j from I to n. I hope it's readable enough. So I maintain the positive elements. So this pos is like the clone of this positives. So this is like the positive elements we can take. We have not yet taken this in a largest k elements. Okay, we have removed the largest k elements from the set. So this is like the choices we have for the positive numbers outside our array. Okay, I hope that makes sense. So we remove this positive number. These are the choices we have outside the array. Again, I'm speaking outside the array. How it will be clearer. And this negative is a heap. So this is a collection of all the negative elements inside the subarray we have taken. Okay. And since sum outer is equal to sum k, and the sum is like the sum of the subarray. So let's go to the implementation that will be clearer what I've done. So I'll iterate over each element from this subarray from I to n. So x is the element. I add it to our answer. If it is positive, then it is possible that it was one of the largest values we have taken. Then we check if we are if it was the largest like if it was considered in our sum k previously, then we remove it from a sum outer and we add the largest value we have so far. So the thought process here is like if I have 1, 5, minus 6, let's say, and 4, and this is the subarray I'm talking about. So my thought process is going to be I will maintain I will maintain the subarray sum I can get here, plus I'm going to add as much as I can from the outside, right? Through the swaps. So like 4 is going to come here. And if there was 7 also, so 7 would have come here outside the array. So this, strictly speaking, I maintain a sum plus sum outer. So this is not necessarily the sum of the subarray, but this is still a sum we can get. So I hope that makes sense. So so sum plus sum outer is is the largest subarray sum we can get if we this subarray as a sum, and from outside also we consider some elements that we can get through swaps. So I in that my thought process is if it is if it was like 1, 5, minus 6 and 4, and I've considered this subarray, then we are not considering 5 from the outside. Currently some outer will contain 5. So I will remove that 5 from a sum outer and I will add the backup uh, outer positive elements from the subarray, from the remaining array. Otherwise, if nums of j is negative, then we will check if the negative length is less than taken. So taken is basically our k here. So taken is equal to k here. I should have just used k, but it's fine. So if it is negative length is less than k, that means there are some outside elements we are going to take in our array. So I ignore that negative element and I push it in the heap for future use. If the negative length is equal to taken, if it is equal to k, so that will go in the else condition because this length will never be positive or never be greater than k. If it is equal, that means we have to take a negative element. The swaps are not enough to remove all of them, but instead of taking the current one, we take the largest element, the largest negative element, the least bad one. So I again remove it from the answer. I push that into my heap, but then I pop the largest value from the heap and add it to my sum. So this is going to be a negative value which we cannot remove from the swaps. So this sum is the good sum we can take from this subarray. So I have ignored minus 6 here because this 4 can come here. So this is going to be like this sum is going to be 6 and this outer sum is going to be 4. So 6 plus 4, if this 10 is greater than equal to target sum, that means a predicate function, a binary search will return true. Otherwise it will return false. So yeah, that is broadly the idea how I have solved it. So this was a nice problem. And I got a few penalties in implementation, but that's fine. So yeah, that's it from my side. Thanks for watching. Bye.